Welcome to Dr. Sherry's Astronomy channel. The topic of this episode is measuring magnetic fields from around the time the universe was born. The universe is thought to have been born about 13.8 billion years ago, through a great explosion called the Big Bang. This theory is supported mainly by three observational pieces of evidence. First, the Hubble-Lemaitre law, which shows that more distant galaxies are receding faster, is direct evidence that the universe is expanding. Next, the fact that the abundances of light elements such as hydrogen and helium formed in the early universe match the predictions of Big Bang theory also strongly supports this theory. And the cosmic microwave background radiation, observed from every direction in the universe, is observed as a remnant from about 380,000 years after the Big Bang, when the universe cooled, neutral hydrogen formed, and light became able to travel freely. Putting these lines of evidence together, it follows that the universe has continued expanding and evolving since shortly after its birth. In other words, at first, what was concentrated almost at a single point expanded at an unimaginable speed, becoming a huge cloud of gas in which matter was distributed almost uniformly. After that, the universe kept expanding, and during that time space became more and more empty, with large voids that contained little matter, while in between there formed large-scale structures of the universe such as galaxy clusters, where thousands of galaxies gather in small regions. When we look at the nearby universe, the distribution of galaxies is not uniform, and we can confirm large-scale structures of the universe such as galaxy clusters where galaxies are densely packed, and line-like structures connecting clusters, called filaments. For example, if we look at the three-dimensional distribution of galaxies obtained by the latest dark energy spectroscopic instrument, it looks like this. The center of the screen is the position of our Milky Way galaxy, which includes Earth. Each dot spreading out radially from there represents a galaxy. This distribution map includes not only positions on the celestial sphere, but also the distances to the galaxies, in other words, information in the depth direction. The Dark Energy Spectroscopic Instrument observed about 15 million galaxies and quasars, and by measuring the redshift of each one, it drew out a three-dimensional structure of the universe like this. This image visualizes a portion of the three-dimensional distribution, cut out in a fan shape. The center is our Earth, and the farther outward you go, the more you are looking into the universe of the past. If you look at the magnified part of the details, you can see how galaxies connect like bubbles to form the large-scale structure of the universe. From this precise map, clues have also been obtained to unravel the history of the universe's expansion and the behavior of dark energy. When we think about the way the universe formed like this, it means that every phenomenon is deeply linked to the evolution of the universe. Among them, magnetic fields are especially mysterious. Earth, where we live, also has a strong magnetic field, and by repelling charged particles raining down from space, it creates an environment where many forms of life can live safely. Such magnetic fields are seen not only on Earth, but also in stars like the Sun and inside galaxies. Furthermore, as observations have advanced, it has also become clear that even in the vast space between galaxies where there are no stars, very weak magnetic fields are spread throughout. So, when and how were the magnetic fields that seem to envelop the universe as a whole born? One leading idea is that seeds of magnetic fields were born soon after the universe was created, in other words, right after the Big Bang. The universe at that time was incomparably hotter than it is today, in a chaotic, energy-filled state where light and particles flew around violently. As the temperature gradually fell, there were many events called phase transitions, in which the form of energy changed rapidly. At those times, a slight bias arose in the motion of charged particles, a flow like an electric current was created, and from that, weak magnetic fields are thought to have been generated. The magnetic fields born in this way were extremely weak, and are inferred to have had only a strength that can finally be estimated with today's technology. However, This faint magnetic field spread along with the expansion of the universe, and later, in the process by which galaxies and stars were born, it was gradually amplified by rotation, explosions, galactic winds, and other effects. As a result, it grew into the magnetic fields observed in galaxies, and is considered to have become the source of cosmic magnetic fields that spread across the universe today. In other words, investigating the universe's magnetic fields becomes an important clue for learning what physical laws were at work in the era when the universe was still just born. So, how can we learn about the magnetic fields from around the time the universe was born? An international research team led by Dr. Marco Pavicevic at the International School for Advanced Studies in Trieste, Italy, took on this difficult challenge. The team developed a new method to estimate the strength of magnetic fields that existed when the universe was born, and carried out a detailed analysis based on actual observational data. The key clue was a light signature called the Lyman alpha absorption line. This is a phenomenon in which light emitted from a huge, distant object called a quasar passes through clouds of hydrogen gas along the way, and only certain wavelengths are absorbed. Because this absorption happens continuously, when observed with a spectrograph, countless thin lines appear lined up in the light spectrum. Because the pattern is densely packed like trees in a forest, it is also called the Lyman alpha forest. In this Lyman alpha forest, the distribution and motion of gas that makes up the universe, and the state of tiny fluctuations that existed in the early universe, are recorded. Therefore, if magnetic fields existed when the universe was born, those magnetic fields should slightly disturb the motion of gas, and should also affect the shapes of the large-scale structures of the universe, such as galaxies and thread-like gas structures, that form later. If the magnetic field is strong, the fluctuations become larger, and if it is weak, the distribution becomes smoother. In other words, by precisely observing the small fluctuations in the Lyman alpha forest and comparing the pattern with theoretical simulations, we can work backward to infer the strength of magnetic fields in the early universe. The research team ran more than 250,000 simulations while changing various conditions, such as the temperature of the universe's gas, the timing of ionization, and the density distribution. Then, by comparing each result with actual observational data and examining which conditions matched best, they estimated the strength of the magnetic field that existed in the early universe. Through this enormous analysis, it became possible to read traces of primordial magnetic fields directly from observations, which could not be understood from theory alone. If we look at the actual analysis results, it looks like this. The horizontal axis represents the size of fluctuations in the universe, in other words, the scale of structure. As the value increases, it means we are looking at fluctuations on finer scales. The vertical axis shows the strength of the dark and light contrast of the absorption lines seen in the Lyman alpha forest, and it can be regarded as the intensity of the fluctuations. Observational data obtained at 3 redshifts are used, and they are shown as blue, orange, and green points. Against these data, 3 types of theoretical models are compared. What is written as lambda CDM is the standard cosmological model widely used today, representing the case where there is no magnetic field in the early universe. On the other hand, the curves labeled PMF consider a primordial magnetic field, and 2 cases are shown where the magnetic field strength is set to 0.2 nanogauss and 0.5 nanogauss. Comparing the results, the lambda CDM model that includes no magnetic field at all has fluctuations that are somewhat weaker than the observed data, and it could not reproduce the fine structures. Conversely, in the model with a magnetic field of 0.5 nanogauss, the fluctuations become too strong, and it does not match the observations. We can see that the 0.2 nanogauss model, which is in between, matches the observational data best. This magnetic field strength is about 1 trillion times weaker than a typical refrigerator magnet, about 100 Gauss, and is so faint that it is close to the magnetic field produced by neural activity in the human brain. Upper limits had also been obtained from observations of the cosmic microwave background, but in this analysis, a value several times to about 10 times smaller than that was derived. This result can be said to show, more precisely than ever before, how weak the magnetic field in the early universe was. Through this study, it was clearly shown that the magnetic field born when the universe was created was weaker than expected. This achievement is not only a measurement of magnetic field strength, but also a major clue for exploring what kinds of physical phenomena occurred in the universe right after the Big Bang. For example, if even a slight magnetic field existed when the universe was born, that magnetic field could have changed how matter gathered and how gas flowed, and could have accelerated the birth of stars and galaxies. In other words, the magnetic field value obtained this time can also become a clue to unravel one of the major mysteries of modern astronomy: when and how galaxies were formed. In the future, by using observational data from the James Webb Space Telescope and others, it is expected that we will be able to investigate traces of magnetic fields in the early universe in even more detail. I'm looking forward to what comes next. Thank you for watching, and I'll see you in the next video. If you enjoyed this video, please don't forget to give it a thumbs up. Hit the subscribe button and the notification bell icon, so you'll be notified when new videos are released.